Hello everyone, I'm Ramya Balasubramanian. I'm a NLP engineer and I work with Chilwell AI as an NLP engineer. Chilwell AI is a startup and they specialize in event recommendation. So I am there to help them in this process of improving the event recommendation using natural language processing. So our topic for discussion is support vector machine. And before I start this highly technical discussion, I would like to start off at a lighter note with an anecdote. So Vladimir Vapnik was the person who came up with this concept of support vector machines, and that's amply clear from the original paper on support vector machines, of course. So he was from Moscow, and he called his friend in the US who worked for Bell Laboratories, and his friend in the US was trying to solve the problem of digit recognition. And if you look at the 1990s, that was a huge challenge, the problem of digit recognition, the 10 class problem that you had. So when he called his friend in the US, the friend, he started saying that, we're dealing with this problem of digit recognition and we're facing a lot of problems, and he was talking about the different algorithms that he was using to solve this problem. And then Vapnik said, why can't you use support vector machines? I wrote a paper on that several years ago, and you'll be surprised that the original paper came in 30 years ago, 1960s, I suppose. So he said, why can't you use support vector machines? And the friend said, oh, are you serious? As always, the friends say, that's not going to work. That's not going to work. So Vapnik was like, he was really hurt. He didn't take it lightly. He said, how could you say that? I challenge you. Use this algorithm and you'll get the accuracy that you want. And so it happened. He used, his friend at Bell Laboratories, he and his friend, of course, used digit recognition to solve the problem of digit recognition. They used support vector machines, and they saw that it was fairly accurate as compared to the different algorithms that they were using. So with that, I start my discussion. So what is the simple idea, the crux of all this? As stated in the paper, support vector machine simply maps the input vectors in an n-dimensional space to a high-dimensional feature space, and the authors claim that using support vector machines, the process is kind of effortless. The computational and the space complexity is not much as compared to the conventional techniques that we use. So there were two selling points that the authors came up with in the paper. The first one was that SVMs are capable of separating, they are capable of classifying both the linearly separable and the non-separable data points, committing minimum errors. So when I say minimum errors, that is in comparison to all the contemporary algorithms that existed at that time, the so-called decision trees and the neural networks, or 2-layer, 5-layer neural networks. And we'll see at the end of the discussion, when I'm talking about the experimental analyses, that how they compare the different contemporary algorithms with their algorithm, SVMs. The second selling point was that SVMs had a very high generalization ability, and there's a way of quantitatively assessing the generalization ability, and we'll be discussing about that in the discussion. And what they meant was they're able to perform these nonlinear transformations on the data in the input space And that is independent, the process, the complexity of the process is independent of the input dimension size and the training data size. And we'll see how that's true in the discussion. So the paper starts off, in the introductory part, you would find all these different algorithms, the evolution of algorithms in the field of pattern recognition. So the author start off with a very, very basic algorithm. I think everyone would be knowing about this. It's the discriminant analysis. So R.A. Fisher in 1930s, 1936 to be precise, he described this process of discriminant analysis. So he said that let's say we take a data model that has two groups of population that are normally distributed, and one set of population is associated with the M1 mean vector and a covariance matrix which is represented by sigma sub 1. And then you have another group of population, again normally distributed, associated with the M2 mean vector and a covariance matrix sigma 2. And then the vectors here are n-dimensional. So the optimal Bayesian solution for this is a quadratic decision boundary which is described by this equation. And author went on to say, R.A. Fisher, he went on to say that if sigma 1, the covariance matrix associated with one population is equal to the covariance matrix associated with the second population, that's just to say that the covariance, the variance within the population is the same for the two groups. We end up with a linear decision boundary because this equation, the above equation, it reduces to the equation below. Actually, you could substitute sigma 1 equal to sigma 2 and you can find out that that's actually true. So we get a linear decision boundary. But then, Fisher, he realized that when you talk about quadratic decision boundaries, you're essentially dealing with n into n plus 3 by 2 parameters, which is a lot if n is a large number. And then he said that, okay, in the case of a linear decision boundary, however, you'll be dealing only with n parameters. So he proposed that why do we have to complicate the process? And there's one more thing that he observed, that as n increases, when we start dealing with a quadratic decision boundary problem, finding the problem of finding this, it's not, the results that we get are not reliable. When we're dealing with an order of n square sort of a problem, the results are not reliable when the data set is small. So he proposed that, even in the cases where sigma 1 is not equal to, sigma 2, we could still make do with a linear decision boundary, and a common covariance matrix could be, it could be computed using this equation where tau is, of course, a constant, and we could actually decompose this problem of quadratic decision boundary to a linear decision boundary. So if you look at all the initial algorithms that were proposed for pattern recognition, they were constructed, they all emphasized on constructing the linear decision boundaries because of this reason.
How do you pick tau in this?
So tau is, of course, empirically picked.
Oh.
So you were talking about 1930s, 1940s. So this was picked empirically. So so the next, in 1960s, Rosenwald, of course, you must be knowing him, came up with the neural networks. Of course, he came up with Perceptron. So he said that Perceptron consists of connected neurons, and each neuron acts as a separating hyperplane. So you're actually talking about a piecewise linear decision boundary here. So, and then at that time, he proposed that the neural networks, only the output layers, the weights associated with the output layers were adaptive, as in adjustable. But it was in 1980s, when Rummel, Hart, Hinton, and Williams, they came up with the the back propagation algorithm, and that's when all the weights in the neural networks, they were adaptive and adjustable. So YSVM. So this is the part of the introduction where the author really discusses about why this concept of support vector machines was introduced in the first place. So you might be thinking, why did I say n into n plus 3 by 2 parameters? This is the proof for that, and they've given it in the paper. So let's say that I am talking about constructing a polynomial of degree 2, and my input vector size is n. So if I'm talking about linear, you can say parameters like x1, x2, x3, then I am talking about computing n parameters, the coefficients associated with linear terms. I have n, and the square terms I have again n, and when I talk about interactions is again nc2. So that's n into n minus 1 plus 2, because I don't want to spend time on this because there's more complicated stuff coming in. So if you add all this, you get n into n plus 3 by 2. So they said that when you have so many parameters to estimate, there are two problems. One is conceptual, the other is technical. So the conceptual problem is that given the high dimensionality of the feature space, how could you build a separating surface which could generalize well? And when we talk about generalization, we are talking about testing errors, like we pick an arbitrary point and try to classify it. So probability of misclassifying that. So when we talk about generalize, of course, we talk about that point not being misclassified. So that was the first problem, the conceptual problem. The technical problem was how would we treat it computationally? It's so expensive. So how would we do that? So how should we treat this high dimensional problem in the feature space computationally? So the author said finally, okay, the conceptual problem, you could solve it using this class of hyperplanes that maximize the margin between the vectors associated with the two classes. So there you go, support vector machines, the widest street algorithm. And the technical problem, they said that, you know what, in order to define the hyperplane, you simply need those support vectors, a small set of vectors called as the support vectors. So you are in a way solving the computational complexity problem. So these were the things that they talked about. And they said, they also claimed that the probability of error, the expected value of that is, it has a upper bound which is given by expected value of the number of support vectors divided by the number of training examples or training vectors. So the authors identified two groups of, or two types of training sets. One set being the one that could be linearly separated, and the one that was not linearly separated, without errors. Sorry, I missed that point. So separable without errors. So that was the first case that they dealt with. And they proposed the hard margin support vector machine for, for classifying this sort of a data. So before I go into the mathematics of the hard margin support vector machines, I would like to refresh people's memory. I know everyone knows about this. So when you talk about a distance di, which is distance of xi, a point xi, from a hyperplane, which is which is described by the vector w naught. That is the direction perpendicular to a given hyperplane, because this could be generalized. We could say that the distance di is equal to w naught dot xi plus b divided by the norm of w naught. Now this formula, or this particular thing, is very important because it's used in the derivations. And you would know that if the distance is 0, of course, this quantity would be equal to 0. I mean, it's for the points that lie on the hyperplane, the distance would be 0, di would be equal to 0. So when we have a data set which is described by the points in the data set is described by the ordered pair y1, x1, y2, x2, and so on and so forth. Let's say that there are L points in the data set, and we say that they're linearly separable, then we could, we could describe the points belonging to the two separate classes using this inequality, the two sets of inequality. So w dot x sub I plus b is greater than equal to 1 for those points that have the label equal to 1, and w dot x sub I plus b is less than equal to -1 for the labels, the points that have the labels equal to -1. And this could be essentially combined. I don't know if one is hiding somewhere, but this is my first equation. So this is the constraint. You can combine the two inequalities in this. Y sub I whole multiplied by w dot xi plus b is greater than equal to 1. So that's the constraint that we would be using in our Lagranges. So here, of course, we are trying to maximize the margin, so we need to understand what the margin is. How do we quantify it? So here's the margin. So let's say that my optimal parameters turn out to be w sub 0 and b sub 0, beta sub 0. Then the margin is described by 2 upon norm of w naught. So this could be derived from all those things that I was talking about, the distance vector and other things. Now you might be surprised. You would be saying, hey, I noticed the 1 and I noticed 2 here. So where did you come? Like how did you say that the distance is equal to 1? Like from where are you computing all this? So this is just a strategy that the authors use to simplify the calculations. So they said that let's have a plane. Let's say that the closest point. So what is a margin basically? If you go to the previous slide, the margin is defined by the vector that is the data point that is closest to the hyperplane. So they said that let that be some quantity. Let that be alpha. So what they did was, let's scale the entire space to alpha such that this distance is equal to 1. So that was purely meant for some sort of simplification of calculations, right? So that's why you see a 1 here, and that they basically scale the space to assume that distance between the closest vector and the hyperplane was 1. And that's how you come up with this 2 upon norm of w sub 0. So what we do is that we convert this problem of maximizing this margin to a convex optimization problem for which we take the reciprocal, and we try to minimize the norm, the square of this norm by 2. So how do we get the square of the norm? We simply take the dot product, w dot w. So that's here. And then we add the constraint that we need to take care of, which is here, and we add the Lagrange multiplier. And of course, all of us know that that basically the Lagrange multipliers are always non-negative. So we then differentiate. In order to minimize it, we differentiate the Lagrangian with respect to w and beta naught, which are the primal variables, and we don't touch the dual variable, of course, because if we do that, we get back the constraint. So we do that, and when we differentiate it with respect to w, we get summation of alpha sub I, y sub I, x sub I equal to w, and then when we differentiate it with respect to beta naught, we get summation of alpha I, y I should be equal to 0. And we substitute this into this equation, and then we get this, and then we simplify it, and we get summation of alpha sub I minus half of the summation of alpha I, alpha j, yi, yj, x sub I dot x sub j. And all this is, now we have represented the Lagrangian, which we would be optimizing at the end in terms of the alpha parameters. And of course, authors have, like I took it from various other papers, but the authors have preferred to give a more mathematical representation. So the lambda is the vector that defines these alpha parameters, the Lagrange multipliers, and it's just the more complex representation of this, or whichever. So you have this particular, the optimization of this with respect to the Lagrange multipliers is again a quadratic programming problem. And these are the constraints that we need to remember, that none of these would be less than 0, and of course the summation of alpha I, yi is equal to 0, represented by this. So now the other group of training set was the one that couldn't be separated without errors, without committing errors. So that's.
Can you go back to the previous one? So in this one, you are differentiating it with respect to W and beta naught to calculate those values. So where are you putting those values? Like, are you assigning those values in the equation above that?
Yeah. So what I'm trying to do, like what they tried to do was they differentiated it. So they got this, and they made it equal to 0, and after that they got this equation, and then the value of W was put here. Okay. So that's what they've done. So the second case where the training said the data points are not separable without errors, they proposed this algorithm, which is the soft margin support vectorization. So they said that let's slightly modify the constraint already present, and let's add this error term. Let's add this error term, which is z sub I, and of course the z sub I is always it's non-negative. So, and then they said that let's define a function that we need to minimize, a function that includes this error term that we need to minimize. So they defined it as phi of z as the summation of z sub I raised to the power sigma I from 1 to L. Now, of course, this is a very complicated thing, that if I have to estimate z's, and then I need to also find out sigma, it turns out to be a NP complete problem. In order to avoid that, they simply put sigma equal to 1. And also that, when you put sigma equal to 1, it has some significance. That it's a summation of, it could be taken as the sum of the deviations of training errors. And here, it's really the sum of, we can take the sum of deviations, because we're assuming that, z sub I is non-negative. So again, they did the same thing, used a Lagrangian. So they included this new, the function that they had to optimize, and they introduced, you can say, a scalar delta, which it was multiplied, and then of course they also included this constraint, that this we want this to be equal to, greater than equal to 0. So that's something that they introduced. So a new Lagrange multiplier, new group of that, lambda sub I, was also introduced. So again, we differentiate this equation with respect to the primal variables like W and beta naught and Z sub I. And then we get this equation as before. We again get this equation, which is summation of alpha sub I y I is equal to 0. And then we finally get this. And this has a significance which I'll go over. I'll talk about it. Before that, I would want to emphasize this, that when they put these equations back into the Lagrangian, they surprisingly got back the same function that they needed to optimize. And then you will ask me, okay, then what was the use of putting all these new constraints into the Lagrangian when you end up getting the same function to optimize? So here's where the soft margin is different from hard margin. So they found out that, of course, when you look at this, alpha sub I plus lambda sub I, the two Lagrange multipliers, the sum of that is constrained by this delta, which essentially means that if this is non-negative, lambda I is non-negative, there's an upper bound that is associated with alpha sub I, and that is defined by delta. So this is what is different about the soft margin support vector machines. So the alpha Lagrange multiplier in the hard margin, if you remember, it simply has a lower bound. It simply has a lower bound here. So in the case where the training data set is, it consists of points that are not separable without committing errors, we define a new constraint, like we add something which is called as an error term, and we add it to our constraint. So it becomes y sub I into w dot x sub I plus b is greater than or equal to 1, and then you have this particular error term added to it. And the authors define that this particular error term is non-negative. It can only take non-negative values. And then we define a function that we need to minimize. The function that is associated with the error term that we need to minimize, and that's phi of xi. I'm sorry if I use some other nomenclature. Please forgive me for that. So this is xi. So phi sub xi is equal to summation of xi sub I raised to power sigma for all the endpoints, of course. So in order to avoid it from becoming an NP-complete problem, the authors proposed that sigma should be equal to 1. And it's actually a natural choice for us, because this, when sigma is equal to 1, it actually turns out to be the sum of the deviation of training errors. So we include that as our, what do you call that, function that we need to minimize, summation of the errors. And then, of course, we start off with this Lagrangian, where we put all the functions that we need to minimize, and then the constraints that we need to take care of. So the summation of xi sub I is introduced with with the parameter scalar delta that we multiply with that, and we have the constraint summation of sigma I with introduced with a new Lagrange multiplier. I'm sorry, lambda sub I. So we differentiate this equation with respect to w, and we get the same equation that we got as before. And then we differentiate beta naught. We differentiate this Lagrangian with respect to beta naught, and we get this equation that is the summation of alpha I yi is equal to 0. And then we differentiate it with respect to xi sub I, and we get alpha sub I plus lambda sub I is bounded by the scalar delta. And then we substitute this into the equation, we substitute this into the main equation, which is this, and we get this function that we need to optimize, which is summation of alpha sub I minus half of the summation of alpha sub I and all this that we got before. So it is same as what we got for the hard margin support vector machine. So what is different about the hard margin and the soft margin support vector machines? So when you look at this particular equation, you find that there is an upper bound on the Lagrange multiplier alpha sub I. So it is bounded by this delta, and this plays a crucial role in regulating the margin, the width of the margin, and that's very important because now we are dealing with the training set that is not separable without committing error. So that is the significance of this, and this is represented by these constraints.
If you go back to the previous slide, then we are saying that we are going to connect that delta to the C over here,
Yeah.
C constant.
Yes.
And then we are saying that if we go back to the side where we were talking about the graph of support vector machine, the hard margin slide, yeah, that's right. So here we are saying that because we introduced the slack parameter, the error variable, and we had a C, so now the problem became more flexible.
Yes.
And,
Yes. So it regulates this particular. So what it does is that it creates an upper bound on alpha sub I, and this regulates the support vectors that we are choosing, and in turn it helps in regulating the margin. So this is that is the difference between the soft margin and the hard margin support vector machines. So now we come to a very interesting part of the support vector machines, which is the convolution of dot products. So usually when we have we have vectors in the input space, and they cannot be separated using a linear boundary. What we do is that we transform them into the high dimensional feature space using a function that we need to know phi. Maybe we use a priori information or some other mathematical tool to determine this phi, and we need to know phi. We do that transformation, and then we try to calculate some sort of a function which could help in classification function. So that's computationally expensive, right? So in case of support vector machines, the authors, what they did was they showed that, let's say that there is a hypothetical function phi which maps R, which maps the vectors in the input space to the high dimensional feature space, and then we could literally substitute it in the function that helps in classification, which is f of x. So it's w dot, the dot product of w and phi of x plus b, and we know from the previous slides that this w is actually equal to summation of y sub I, alpha sub I, phi x sub I. Okay, so here the x got replaced with, it replaced by, the phi of x. And then when we substitute it into this equation, f of x, we get that ultimately what we want is just the dot product. We are only concerned about the dot product of phi of x and phi of x sub I. So they said that, why do we do this? Like, why do we first, take it to the feature space and then, calculate this dot product? Why can't we have simply a function which would k of u and v, where u and v belongs to the input space, it directly, takes care of, transforming this to the feature space and calculates the dot product. So essentially a function which he called as the kernel function said, it did two things. It solved two purposes. First is it took the vectors to that feature space, and then, it basically performed the dot product of that. So the only thing that we need to take care of is this, and finding out what this k of uv is. And they found out that any function that satisfies the Mercer's equation could be used as they called it as a kernel function. And that is where, they said that probably we could take x and y, u and v, which is in the input space, and take it to the Hilbert space, perform the dot product, and then we could simply use it in our classification function. So they just simplified the process of classification. And of course, there are different kernel functions that you might have heard of, the polynomial kernel function, the radial basis function, and all. So that was the genesis of that. So now we come to the general features of support vector machines. The first thing is that they claimed that constructing the support vector machine is efficient. Now, how did they say that? You'll always have that, oh, this is a quadratic programming problem. How could you say it's efficient? So they said that you can take the data, instead of taking the entire data in one go, what you could do is that take a subset of that data, calculate the support vectors, and then isolate those support vectors, again put it back into another subset of your training data, and do this process till you exhaust all the points in the training set. So essentially what you're doing is that you are breaking up the problem of dealing with a huge training set to smaller intermediate steps. So that's one thing that they've proposed in the paper, and they say that they refer back to that particular method that they were describing, while saying that constructing support vector machines it's an efficient process. The second thing that they said, that since they're using this kernel function, they can be extremely flexible, and with the a priori information about the data set, they can build the kernel functions that they want, or they could design the exact kernel functions according to their problem, and that would make it a universal machine. It could deal with any sort of data set, any sort of problem. So that's how they said that support vector machine is a universal machine. Now this is the part which needs some explanation. So they said that support vector machines could control the generalization ability. Like I said before, generalization ability has to do with the testing errors. So when you have, when I know most of us do a lot of modeling, and we know that when the training data, the training errors are large as compared to the test, or comparable to the testing errors, we know that we are talking about an underfitted model. And when the testing error is very high as compared to the training error, we know that it is a problem of overfitting. So,
overfitting is when the training is very high as compared to the test, right? Is that what you meant?
Testing is high as compared to training, because you have fitted your model according to some training data, and it's exactly predicting, it's going right, it's predicting everything correctly for the training set. But then when I bring something from outside, which is my testing set, it's not able to predict it with.
That's what I said. Yeah.
So its testing is higher, testing error is higher.
Oh, testing error.
Yes. Is higher than the training.
Everybody else got it right?
Yes.
Oh well. Carry on.
I got confused in between. I said something wrong. So basically, we define the testing error, which is the risk associated with the classifier, with the errors associated with training, which we call it as the empirical error, and we relate this with an upper bound, that this would always be less than equal to the training error plus this bound, a soup of variables, of course. But then, when I looked at this initially 2 years back, I was like, oh my God, this is so complicated. How would I be ever able to remember all this and explain it to people. So, of course, so at that time it was like explaining it to the recruiters, of course. So if at all they ask me this question, but then, but then I read some papers where they said that this could be simplified, or it could be approximated to the root of the VC dimension. This is VC of VC dimension is always associated with the classifier. VC dimension divided by n, which is the size of the training set. So they said that in case of support vector machines, this particular VC dimension is the Wapnick-Chervonenskis, if I'm pronouncing this correctly, dimension. It's actually equal to r square at the dot product of w dot w. And we know that we are actually minimizing this quantity when we're building the support vector machines. What is this r square? So r square is the radius of the hypersphere that encompasses all the training points, right? So let's imagine a space where you have all the training points and you have a sphere that encompasses all those training points. So it's radius of that particular sphere, hypersphere. And of course we by selecting the right training data, we could control this parameter. So in a way we control this, so we control this, which is also called as the generalization error bound. And what the authors proposed was that we can control this, like the support vector machines can control this generalization error bound. So that's the third thing that they said is great about support vector machines. Now we go to the last part of the presentation, where we discuss the experimental analysis that was carried out by Wapnick and Cortes. So they carried out two experiments. One was the two types of experiments, of course. So in the first type of experiment, they constructed an artificial set of patterns in the plane, and they used the second order polynomial decision boundary. So if you remember the kernel function u dot v plus 1 raised to the power d, where d is 2, so it was that function. And then in the second experiment, they took the real life problem of digit recognition. So they took various data sets that dealt with the problem of digit recognition. So in the first type of experiment, as I said, they used this kernel function, and they used visualizations to illustrate the power of the algorithm. So these are the visualizations they came up with. So if you look at the crosses are the misclassifications. So the white dots are, of course, the dots belonging to one class, and the black dots are belonging to the other class, and then these highlighted points with the circle are the support vector pattern. So they claimed, that the errors that were the errors of misclassifications committed by this support vector machine, the second degree polynomial, constructed out of the second degree polynomial kernel function, was less than, or was the least as compared to all the second order decision boundaries that were drawn using the contemporary algorithms of the time. And then the second in the second type of experiment, of course, they took the real life example of digit recognition. So there are two types of data sets that they used. One was the USPS database, which was a smaller data set with 7,300 training patterns and 2,000 testing patterns with a resolution of 16 cross 16. And they tested this particular data set with polynomials, the kernel function, the polynomial kernel functions of various degrees, essentially from 1 to 7, as we'll see. And this particular NIST database, of course, consisted of 60,000 training and 10,000 test patterns, resolution of 28 cross 28 resolution. But because of lack of time, they only had 2 weeks to carry out this experiment. So they were happy with the 4th degree polynomial classifier that they developed for this. and they compared the performance of this fourth degree polynomial with the contemporary types of learning machines like the decision trees, 2-layer, 5-layer neural networks, and of course humans. So
Was this also 60s or more recent?
no, this is recent.
95?
95?
Yeah.
95. There is C4.5, like those are newer algorithms. If I'm not
Yes. Even this neural networks. So, so this USPS database, of course, this is the table that they have given, where they say that the raw error rate is, if you see, for these algorithms is 2.25 for human performance. Of course, we could never beat that at that time, of course. And the CART, and then you have the C4.5, 17 and 16 respectively, and the 2-layer neural network 6.6, and this was the 5.1, of course, was the neural network that was specifically designed for the task of digit recognition, and that had 5.1, and they did it as I mentioned, they tried out all the polynomial degree functions from 1 to 7, and they were very happy because of course they were not happy about the linear, the one with the degree equal to 1, but they were happy about all the polynomial degree functions from 2 to 7. So they said the several observations that they made. First thing was that even the second degree polynomial kernel function performed better than the neural network. So they were very happy about that. The second thing that they said was that if you look at the number of support vectors associated with these polynomials, it increases gradually. Doesn't increase too much. So it increases gradually from the 2 degree to 7 degree, and this is just to emphasize the point that the computational complexity does not change much with the input, with the functions that we are using and all that stuff. So it doesn't change. It's very marginal change in support vectors. Because it does, when we talk about the degree of polynomial, of course the dimensionality of the feature space is changing drastically, but you can see the support vectors that are used to define the hyperplanes are not changing. It's very gradual change. So that's another thing that they pointed towards. And of course they also talked about the generalization ability. They said that the upper bound that they calculated for this still holds. The theoretical upper bound that they have for generalization still holds for this.
Why is it like the maximum for linear relationship? Like if you go back, the number of supporting vectors is the maximum is for linear relationships.
Yeah. So in the paper, that's a very good question. So this, so they said that this particular problem is not could not be essentially dealt with a linear sort of polynomial and sort of a function, and that's exactly why the support vectors are very high. So they actually considered this as an anomalous case. So that's a very good question. I forgot to mention that. Thank you. So of course they also did it with the NIST database, and then they were very happy quoting Jan LeCun, who says that I tried my best. I developed this 5-layer system, but it could not perform as well as the 4-degree polynomial of Wapnick and Curtis. So it seems that they mentioned that, and it's a part of the paper. So that's the thing. So I conclude.
Before you conclude, the Jan LeCun, are you referring to the original CNN when you talk about?
Yes.
Jan
So
LeCun?
the 5-layer network. I'm not sure about that, but the 5-layer network. They say that because they specifically mentioned that this 5-layer network that we are talking about was developed by Jan LeCun, and I can't confirm. I'm sorry.
I know that he worked on the original NIST data set and for
Yes.
the same but I know that it was patented for quite a few years
Yes.
before you could actually.
I think it was Lynette. I think you're right because it was 5 layers.
Yeah, it was the Lynette
So,
also.
yeah.
It could. Okay, then it was the original Christina.
Yeah,
Anyhow,
so
that's our guess.
But they have specifically, like I said, quoted that Jan LeCun, he was like totally, I don't know, awestruck by support vector machines, performance of support.
Nice.
So I conclude this discussion by highlighting 3 ideas. So there are 3 ideas that are important from the standpoint of support vector machines. So one is the solution technique from optimal hyperplanes, the maximum margin, maximizing the margin, the class of hyperplanes that maximize the margin. Second idea is that of convolution of dot products, and the third notion is of the soft margins, which allows you to deal with training sets that couldn't be classified without errors.
Thank you, Ramian, for that. Now we open this for questions because we already have our break. So, any questions?
So I think one was about the current state. So we are saying that support vector machines as of that time look like it's a great model compared to some neural networks also on some specific problem. But as of now, we would say that it's not as great compared to say a deep learning technique when image recognition comes into picture. Is that something you would say?
You should. So,
Could you quickly summarize the question?
So what he's asking is that in 1990s, the support vector machines, they were considered as state of the art. But then now that we have deep learning techniques and all, it's not considered as state of the art. And he asks me. So I would say that even if they were able to deal with the problem of complexity from the standpoint of the feature space and all, I would say that always when you look at support vector machine, it's a kind of a divide and conquer process. So what happens is that you are talking about, classifying one group of points against all the other points. So it's one versus all. So I have, when I've used SVMs, it's been my personal experience that it doesn't scale well when the categories start increasing, the number of categories start increasing. So in the typical the typical the recognition problems that we deal with right now, you talk about 40 classes, 100 classes. I have myself dealt with 300 classes. And I was trying to classify cars and all using image recognition. So you're talking about a lot of categories, and that's when SVM doesn't scale well.
So you're saying that when there's a one versus all, it essentially becomes a very unbalanced situation because of one versus all the categories combined together, and that one will have less instances.
Yes.
And SVM doesn't handle.
Yes, and also that it doesn't deal those multi-class problems well. That's been my experience. If people have had other experience, they can tell me. But that's the part of SVMs which probably have made people start looking at other algorithms, especially the deep learning ones.
Interesting. I've used SCM on smaller class sets, and it performed well. The thing that I noticed about them is just they're super fast as compared to simple neural nets, not even like layers and layers, but like if you connect fully connected layers with not too many parameters. That's why I appreciate them in the past. But that's interesting. Has anybody else faced that, like using a lot of because I think for a lot of classes we were confident enough to do that when deep learning sort of took off and sort of re-emerged. But has anybody else tried SVMs on sort of many classes? Yeah.
I've had good results with linear kernel and high class numbers. So classes up to 200.
Oh, that's That's interesting.
What was the size of the data that you were dealing with?
Yeah, the data sets would be maybe, say, a couple of thousand.
Great. That's the other thing.
That's
So-
small.
yeah, so that's the other thing. With SVMs, I've noticed when I have smaller data set, it just scales better as compared to neural nets.
Yeah.
Because obviously you need a lot of, for all those parameters, you need just more data.
And also it has better generalization properties. It has like theoretical guarantees and
Sure.
generalization.
Sure, yeah.
Do they, in this paper, do they get into the multi-class trade-off of having one versus one and one versus
They didn't.
many?
They didn't.
All? No.
They didn't. Because I actually used SVMs, and you're right. Linear SVMs performed better than the kernel SVMs, but still it was bad as compared to the techniques that we use right now. It was bad. Of course, our natural choice would be faster RCNNs or something
Sure.
like that. So we will never think of SVMs when we're talking about object detection.
That's true. Yeah, and also, okay, just one, yeah, go ahead.
So SVMs, they get theoretically some generalization bounds, right? But in practicality, why does SVM have a bad reputation of being overfitting? Generally what you hear about SVMs are, they overfit a lot. So.
I think I've not faced this, so I'm not able to visualize it, because I've always seen this, that whatever sort of error rate I get, the training is approximately the same, because when I deploy it, I actually look at, for the first time I look at the testing, the true testing error. It's not very different, but then you could say that again it's the problem of all these complex algorithms, because always if you see that when we start defining, like it's a problem of variance versus bias, where the model, when it becomes complex, especially when more to do with the kernel based approaches that we have here, when the model becomes more and more complicated, that's bound to happen. But then what happens is, I'll show you what happens when you start doing that. So when you start making the model more complex, where's my output? So when I start increasing the complexity of the model, like I told you, this log terms could be essentially, you could just neglect them, and it's just that root of VC dimension. These things start gaining significance, the training data size, and then this delta, which is the error probability, all this starts gaining some significance. And at that time, of course, the generalization bound might not hold. So that's where you start seeing that theoretical versus the practical scenarios. Of course, the practical is different.
I can take another shot and just add on to what I felt is that when it normally overfits, it tends to draw more supporting vectors, and more of those categories. If it does that a lot, then it starts overfitting. So maybe that data itself is such that it's not as well separable, and it's drawing a lot of support vectors, because of which that overfitting.
Yeah, that's a very correct observation, and you could see it here. I told you, right, the linear case was not the ideal case, and that's where the support vectors were equal to 200. So it's exactly, he's right. So whatever he said, it's supported by this.
Yeah, so I raised that concern in a conference, and then the answer to that, which was also my answer somewhere else, to the same question, was that, well, it's highly dimensional data. Like, you can't really visualize it well, and you're cutting through space in different dimensions. So is this do still our vision of linear separation apply the same way? Probably not exactly the same way. Anyhow, just food for thought.
It was an artist.
Yeah, so I haven't used SVMs in like 6 years, but I watched a month ago with Lex Friedman, an interview with Vladimir Patnik, And Optic was kind of saying, you know, he's challenged people to come up with this better statistical learning theory, and nobody to date has done it. But on the other hand, it seems like all the deep learning techniques for a lot of different domains give much better predictive accuracy. So I'm kind of wondering where like SVMs are relevant today, and if they're kind of just like a theoretical groundwork that we have in the machine learning field, and if like you can just view them more like an analytical expression for a differential equation versus like an integral or something.
I would say that, you know, like the reason why I chose this topic, because all of us are running towards deep learning. We are essentially forgetting these algorithms. But then, you know, I would say that the performance of an algorithm is, it depends on the type of data set you're choosing. And it's very bad to say that the algorithm that has worked in the field of bioinformatics, biological sciences, and in so many other fields, has stopped having any, you know, it stopped having any significance. It cannot be used. We can't say that because it has worked out for some domains. So I would say that it depends on the type of problem that we are trying to solve and the type of data set that we have.
Have you seen anything recently where it's been used? Since I've only seen like in the last year of all the papers I read, maybe like 3 or 4 things in particular where they chose to use SVMs and got good results.
So I can point you something to you, like how many papers do you know that use integrals?
Pardon me?
How many papers do you know about integrals or about any calculus?
A lot.
No, there's a lot that uses, but
Yeah.
not a lot that just focus on that.
Yeah.
Many papers in machine learning just use it as a tool now. This is a classical.
Yeah.
It's super fast.
Yeah.
It's also good just as a baseline. Like,
Yeah.
try it as a baseline. A lot of people use it, just maybe don't publish it. Because they're like, oh, like, my deep learning model is better than SVMs. Good, so I didn't totally mess up my deep learning model.
So also deep learning. So we had a problem applying machine learning in general to highly unstructured data, and hence deep learning gained momentum because it could really do well on unstructured data, such as speech and image. I'd say if you go to structured data again, there is no guarantee that deep learning usually beats because it's just much more structured. So in that space, I think still traditional algorithms do here and there outperform neural nets, and for a lot of times neural nets is just overkill for those algorithms.
I guess there's also the interpretability part too, right?
That don't get me started on that. So
we can
yeah.
get a conversation on
Yes.
another time.
But
There's a bar downstairs
short
that we can
version, I
continue.
disagree that neural nets are interpretable. I disagree with that statement.
Yeah.
I think it's people have been misinformed. And then long version later.
Okay, I have a question, and I can't hear myself. That's kind of weird. I have to. Okay, sorry. I have to guarantee my voice will capture. Okay, so I've seen weird hybrids where you have a neural net, and you train it, and I think what they did is like they take out the last layer, and then they kind of what would they do? They supplant SVM in the end. I still don't know why they do that. Like, it's like, does anybody know why? What's the rationale for this kind of architecture?
Yeah, you want to. So, like, you can always think as the last layer as you're creating an embedding that puts the data in a more structured way. Until it has more structure, you can use SVM or classical techniques to do whatever task you need to do. It's just like you start from unstructured data, you give it some structure, and then you apply classical.
But how do you know that the last layer the output of the last layer will produce structured data? I guess that's outside of real
It usually
numbers.
depends on the loss function. Like the loss function is saying like the representation of the data that I have is the best possible representation for the task defined by the loss function. So once you have that representation, you are forcing the structure via the loss function.
Okay.
Yeah. So traditionally, it speaks to our traditional machine learning algorithm. Traditionally, we feature engineer things. We got the feature. On top of that, we applied our classifiers, and we knew that those features are directly applicable to the task. So you can think of your neural network as a feature extraction algorithm. You get your features that would be useful, and that's basically what the fully connected layer at the end of most of or the softmax layer at the end of most of neural nets algorithms do.
And this is mostly happening in transfer learning, right? When you have all the layers that they work as a feature extractors, and then you have these classifier at the end.
Okay.
It's the kind of transfer learning, I guess.
Any other question / comment? No? Listening? Oh, sorry. One more?
Yeah, just one quick question. Thanks for the presentation. In the paper, they do a comparison between support vector machines and neural networks, and they claim that in the worst case scenario, support vector machines have been outperforming the neural networks in terms of the time-wise. So my question is, is there any relation with the dimension of the data? Because what they are doing here is fairly small images that they are passing to their support vector machine algorithms. So what will happen if because what they have here is 20 by 20 images or 50 by 50 images, well, what will happen if the dimensions gets bigger? If we have a real image, 1024 by 500. So, what will happen there? Is it still in terms of the time? Is it going to still outperform?
So could you could you be more precise in your question, because I don't think I understood your question.
So the data set that they have here is small images, it's 20 by 20 images. So what will happen if these images they get bigger? Like if we have a 1024 by 514 image.
Okay, I got you.
Is it still gonna outperform neural net?
So I have not per se used it. I've used it in NLP tasks, the support vector machines, but I have not particularly, used it for very big images as such. So, but what they claim in the paper is exactly that. If it doesn't really depend on the input dimensions as such, the complexity, it says the algorithm does not depend on it. So theoretically speaking, it should not affect. I don't care if it's 16 cross 16 or 28 cross 28 or 400 cross 400. I don't care. That's what they say. But then practically, like I said, I have not used it. I've not used very huge images and tried to classify it. So I'm not in a position to answer. Does it really have an effect in practical life? But then it is, according to the paper, it shouldn't.
So I have a question, maybe it's related to that one. So in neural network, when we have lots of data and lots of layers, we know that it's complicated and everything is complicated. But here, when we have few data, we usually know that the polynomials won't work. At least in my cases, I had to use Gaussians or RBFs or those kind of kernels, which are data dependent. So the larger my data, the larger the kernel. So the computation of kernel becomes so huge. So we cannot say that it is very fast anymore. So it becomes highly
yes, I have
data
experienced
dependent.
that. Yes. When you talk about larger data sets, is exactly right. When I was doing this NLP task, I was dealing with huge data sets, and he's right. It takes a lot of time. I was sitting in front of my laptop forever, staring at it, and no output for a long time.
Very problem.
So that is true. That I've seen. With
Sorry,
the
when you say large, you mean the number of data points, or the
the number, because it becomes like data dependent. The kernels, you have to calculate these huge kernels.
Kernels.
Okay. Yeah.
You're talking about memory, right?
I'm talking basically like RBF, which is you have to calculate all these pairwise distances.
And also one point that I would like to add, to to Ehsan's point about unstructured data and why neural networks work better on unstructured data is because, it's just the process. We are not talking about defining functions, kernel functions and all. We're coming up with a function based on the training process. So when we have a structured data, we cannot think of any, I can't say, okay, the polynomial of degree 7 will work or 8 will work. But through the process of training, my neural networks are able to come up with some arbitrary, some complicated function, which is able to finally do the classification well. So that's exactly why, the deep learning techniques have gained significance over, the support vector machines, because they are, good at dealing with these unstructured data, the data for which we don't know what the features will be. So that's essential, you could say, reason why people are now, for structured data, their analysis, they're moving towards